Well, if you recall in our last video, I was talking about the remainder theorem. And if you recall, the remainder theorem stated that, well, if we were to substitute in some value of x, carry out our synthetic division and get the remainder right here, we found that the remainder was equal to the value of the function at x equals c. The factor theorem takes this a little bit further. It says if we have a polynomial that has a factor of x minus c, and this factor is x minus c if p of c is equal to 0. In other words, the remainder is 0. Then the quantity x minus c is a factor of p of x. Well, that's really, really useful. We can check out many factors very quickly using our synthetic division and the factor theorem here to determine whether or not these binomials are in fact factors of p of x. So let's try this out right here. Is x plus 1 a factor? Well, let's check out our synthetic division. And in our synthetic division, we're going to set up our synthetic division bar right here. We're going to substitute in negative 1 outside of the bar. Recall that when we do that, we're just putting in x plus 1 is equal to 0. That means x equals negative 1. And we're going to check it out using our polynomial p of x right here. So we're going to have 1x to the 4th minus 8x cubed plus 22x squared minus 29x plus 24. And we're interested in finding what happens to the remainder. If that remainder is 0, then x plus 1 will be a factor. Otherwise, it isn't. So let's see. If we carry out x equals 1, let's see, we bring down the 1, multiply, negative 1, add down the column to get negative 9, multiply negative 1 times negative 9 to get positive 9, add down the column, 22 plus 9 gives me 31, multiply by negative 1, negative 31, add, going down the column, that's 0, that's 6, that's negative 60, add, multiply negative 1 and negative 60 to give you positive 60, add going down the column, 84. Well, what we've just found is that p of negative 1 would be equal to positive 84, not 0. So we can say that x plus 1, as a result, is not a factor. But we did get a little bit of useful information right here. But we'll save it for later. All right, what happens with x minus 3? Does that work? Well, let's set up our synthetic division again. We're going to put positive 3 on the outside of our division bar here. Along the upper row, the coefficients of p of x, which are 1, negative 8, positive 22, negative 29, and positive 24. That's a 4, trust me. And then we're going to carry down the 1, multiply by 3, add down the column to get negative 5, multiply by 3 to get negative 15, add down the column, that's 7, multiply by 3, that's going to give me 21, add down the column, that's negative 8, times 3, that's negative 24, and sure enough, that gives us a remainder of 0. And we found that, according to this theorem, that x minus 3 is a factor. Now you might be wondering, well, why is it a factor? Well, what that means to us is that p of x, the original function, could be rewritten as the divisor, x minus 3, times the quotient polynomial, in this case, x to the 3rd minus 5x squared plus 7x minus 8. Now, remember that in our division algorithm, we could have written plus 0 right here, right, as our plus the remainder. But if that remainder right here doesn't make any difference, well, we don't usually write that. How does this help us? Well, if we were interested in factoring this polynomial, any other factors that were left over would be part of what's called right here the reduced polynomial. And so if we are interested in finding zeros of a polynomial, we can use this reduced polynomial to help us out now, because x minus 3 as a linear factor, well, it's already factored out. So that's a really useful thing for us, and we'll use that. More to come.